Now let us see the next topic, partial orders. A relation R on a set A is said to be partial ordering relation or a partial order on a set A if R satisfies reflexive, R satisfies antisymmetric, also R must satisfy transitive on the set A. Any relation R satisfies three conditions, reflexive, antisymmetric and transitive, then such a relation is called as partial ordering relation or simply partial order on A. Now what do you mean by partially ordered set, or in short we say poset? A set A along with a partial order R defined on it is called partially ordered set, or an ordered set or a poset, which is written as this structure, that is A comma R. A set A with a partial order R is called poset. Now next is Hasse diagram. Now let us see how to make Hasse diagram. Hasse diagram is a digraph of a partial order obtained from the following steps. First step is eliminate all loops in the diagraph of a partial order. So we need to delete all loops first. That is the first step. Second step says eliminate all the transitive edges in the diagraph of a partial order. We need to eliminate all transitive edges. That means suppose there is an arrow from A to B and there is an arrow from B to C and there is an arrow from A to C. See, what we can see here is transitive property A comma B, B comma C, therefore A comma C. Now what this second step says is remove this transitive edge. Remove this transitive edge. We need to remove all transitive edges from the diagraph. This is the second step. Then third step says rearrange the position of the vertices in such a way that the direction of all the edges point upward. We need to rearrange the vertices in such a way that every edge will look like going upward. Every edge, every arrow will be in the upward direction like this. We need to rearrange the vertices in such a way. Then the next step is last step, remove the direction of all the edges. We need to remove the direction of all the edges. Let us take an example. The diagraph for a relation on the set A is shown below. So this is a diagraph for the set. We have a loop from 1 to 1. Similarly, we have 1 to 8 an arrow. So we write 1 comma 8 in the relation. We have 1 to 2 an arrow. We write 1 comma 2 in the relation. Similarly, we collect all the ordered pairs with the help of this diagram. With the help of this diagraph, write down. We write R. In this R, we can check R is reflexive. That means for every element we have a loop. 1 comma 1 is there. Every element is related to itself. 2 comma 2 is there. 3 comma 3. 6 comma 6. 8 comma 8. So therefore it is reflexive. And it is transitive also. You can verify that it is transitive also, because you can see here we have 1 to 2 an arrow and 2 to 2 an arrow. Therefore we must have an arrow from 1 to 2. Yes, we have this itself. This is our 1 to 2. If you go for the next order pair, we have 1 to 2, 2 to 6. So we expect 1 to 6. 1 to 6. Yes, we have this. So transitivity property holds true for all the elements in R, and it is antisymmetric. Why it is antisymmetric? If you find A comma B in the relation, B comma A will not be there. See, here we have 1 comma 3. We don't have 3 comma 1. Here we have 2 comma 8, but we don't have 8 comma 2. If such a case is there in the relation, then we say it is antisymmetric. Therefore, R is a partially ordered set. R is a partial order on A, and A comma R is a partially ordered set. So first part of the question over. Now we go for the second part of the question. We need to make Hasse diagram. For that, first we need to draw the diagraph of the given relation. Anyhow, in the question, the diagraph itself is given. Let us follow the steps now. First step is remove all self loops. That means we need to remove this loop, this, and this. Let us remove all these self loops and rewrite the diagraph. Yeah, here we have written. We have removed the self loops. See, 1 to 1 there is a loop. We don't have here. Right. So we have removed self loops. Now what is the second step? Remove all transitive edges. Remove all transitive edges. Which are all the transitive edges? 1 comma 3, 3 comma 6 is there. So the transitive edges for this is 1 comma 6. See, this is a transitive edge. We need to remove this. And one more, 1 comma 2 there is an arrow, 2 to 8 there is an arrow, and we have an arrow from 1 to 8. It is like A to B, B to C, then A to C. So transitive edge is 1 to 8. We remove this edge. Yes, that's all. Only two transitive edges we have. Let us remove these two transitive edges and rewrite our diagraph. See, we have removed this and we have removed this transitive edge to get the diagraph as this. Now what we do, what is the next step? We need to rearrange the vertices in such a way that all the edges direct upward, direct upward. That means we need to select the vertex whose in degree is 0, whose in degree is 0. Which is the vertex here whose in degree is 0? Yes, 1. See here, because all the arrows are going outward from this vertex. So there we will take it in the lowest position. We will take it in the lowest position. Then next level will be 2 and 3. Then the next level will be 6 and then 8. Let us rearrange. Let us rearrange. I have taken the same diagraph here. Arranging the vertices so that the direction of the edges point upward. Yes, we can see the vertex whose in degree is 0 has been taken in the lowest place. Then the vertices which are adjacent to 1 we have taken to the next level. And the vertices which are adjacent to 3 and 2, that is 6 and 8, has been taken to the another level. Now you can see every arrow is directing upward. See, it is also upward, upward, upward here. Again this is also upward, this is also upward. And you cannot take this, the vertex 8, and right here you cannot do this, because the direction of the edge will be downward then. The direction of edge will be downward. This should not happen. That's why we have written 8 in this place, so that the edge from 2 to 8 looks upward direction. Now what is the next step after this? Removing the directions of the edges, because it is understood that every edge is moving upward. So it's of no use keeping the arrows. It is understood because every arrow is going upward. So we can remove the direction. We can make it as directionless. Let us remove these directions. We will remove these directions. Only write edges. After removing all the directions, we get the final Hasse diagram as this. So this completes the problem. Now let us take the next problem. If R is a relation on the set A given by 1, 2, 3, 4, which is defined by x is related to y if and only if x divides y. They are given x is related to y if and only if x divides y. Then we have to prove that a comma r is a coset, and then we have to draw its Hasse diagram. Given a set A and also given the relation x is related to y if and only if x divides y. Therefore R is given by set of all ordered pairs x comma y such that x comma y belongs to the set A and x divides y. Whenever x divides y, we have to take such a pair inside our relation. We know 1 divides 1, therefore we have taken 1 comma 1. Also we know 1 divides 2, 1 divides 3, 1 divides 4. So in this set, 1 divides itself, 1 divides 2, 1 divides 3, 1 divides 4. That's why we have taken all such pairs. Now what about 2? 2 will not divide 1. 2 will not divide 1. So we cannot take 2 comma 1. And we also know that 2 divides 2. 2 divides 2. Right? 2 divides 2. So we can take 2 comma 2 in the relation. 2 does not divide 3. 2 will not divide 3 because 3 is not a multiple of 2. So we cannot take 2 comma 3. And 2 divides 4. We know that 2 divides 4 because 4 is the multiple of 2. So I can take 2 comma 4 in the relation. 2 comma 4 we have taken. Then 3 will not divide 1. 3 will not divide 1. So we cannot take 3 comma 1. 3 will not divide 2 also. We cannot take 3 comma 2. 3 divides itself. 3 divides itself. So I can take 3 comma 3 in the relation we have taken. And 3 will not divide 4 because 4 is not a multiple of 3. So we cannot take 3 comma 4 in the relation. Then 4 will not divide 1, 4 will not divide 2, 4 will not divide 3, 4 divides itself. So we can take just 4 comma 4 inside the relation. So using this condition for the relation, we explicitly found all the elements of a relation. Now we need to prove this relation is a poset. It is clearly seen that it is reflexive because loops are there for all the elements, and it is antisymmetric because if 1 comma 2 is there, 2 comma 1 is not there, and 1 comma 3 is there but 3 comma 1 is not there. 1 comma 4 is there, 4 comma 1 is not there, and 2 comma 4 is there but 4 comma 2 is not there, except the self loops. It is happening for all other elements. Therefore it is antisymmetric. It is antisymmetric. Now let us write the lines of the proof. That is to prove A comma R is a poset. First case, we need to say R is reflexive. Yes, we know that for all elements in A, we have loops. Therefore, we can write like this: in R, A comma A belongs to R for all elements A belonging to A. Now to say it is antisymmetric, in R for distinct elements, if A comma B belongs to R, then B comma A does not belongs to R. That is, if 1 comma 2 is there in the relation, then we don't have 2 comma 1 in the relation. 2 comma 1 does not belongs to R. If this is the case for all ordered pairs in the relation, then it is antisymmetric. and the condition is A should not be equal to B, like 1 is not same as 2. So we proved that it is antisymmetric. Now to say it is transitive, whenever A comma B belongs to R and B comma C belongs to R, we observed that in the relation A comma C will also be there in R. We just write in lines. Therefore, R is a partial order on A. So these lines we need to write to say R is a partial order. Hence, A comma R is a poset. Now we go for Hasse diagram for R. We start with a relation. First, we write the diagraph of this relation, which is given by this. We take the vertices 1, 2, 3, 4, because 1, 2, 3, 4 are the elements of A. Then by looking at the relation, we make the diagraph. We already know how to write the diagraph using the relation. Now very first step is remove all self loops. First step is remove all the loops. Let us remove all the loops first. After removing all the loops from this diagraph, we get this diagraph. Then we need to search for transitive edges and delete. What are the transitive edges? Are there any transitive edges? Yes, there is one transitive edge, because there is an arrow from 1 to 2 and there is an arrow from 2 to 4 and also there is an arrow from 1 to 4. So the transitive edge is 1 to 4. We will delete this transitive edge in the next step. Let us do it. Remove all the transitive edges. See, we have removed this transitive edge which was here. We have removed it. Now next step is arrange the vertices in such a way that all the edges direct upward. For that, we need to select the vertex whose in degree is 0 and keep it in the lowest position. Which is the vertex whose in degree is 0 here? 1. Whose in degree is 0. That means no arrow is coming inside this 1. All the arrows are going outward. So let us take this vertex and keep it in the lowest position. The next level will be the vertices which are adjacent to 1. Then the next level will be the 4 which is adjacent to 2. Let us write down this. Yeah, as I said, we have taken 1 in the lowest position. The vertices which are adjacent to 1 to the next level, then the vertex 4 to the next level. So we are done with this. Now the last step is, since all the edges are going upward, we can remove the directions. We can make this diagraph as directionless. Let us remove the directions and rewrite the graph. Remove the direction of all the edges. After removing the directions, we get this, which is a Hasse diagram of the given relation. With this we have completed the problem as well as the module also we have completed.